If you have colleagues who are out in the hallway, drag them back kicking and screaming. We've got a quick celebration, and then we're going to get started with the last portion of our talks around science and technology. So again, go out in the halls, grab people, drag them back in here. They have no choice. All right, so we mentioned it yesterday, but CSAT does not exist without all of you. But as importantly, it doesn't exist without our sponsors. So again, there have been a lot of really great organizations who have supported the Cold Spray Action Team and this organization and all of you here. But especially, we really want to thank our platinum level sponsors who have contributed above and beyond. So we'll be celebrating Centerline tonight. They will have all of the drink tickets if you're looking for a free beverage. But in the meantime, I just want to bring Wally and Julio up here to receive their sponsorship plaque, and also cue up a quick video celebrating Centerline and some of their accomplishments. So if you guys come on up, thank you.
I guarantee it won't be as funny as yesterday's video.
We're counting on it.
His turn.
Thank you, guys.
SST, which is a cold spray technology, is a process by which we can deposit metal particles and make a continuous coating on any kind of a substrate. That gas stream basically picks up the particle and accelerates it such that when it hits the substrate, you get mechanical bonding.
It's a layering process, really, and once it's layered up, It can be instantly machined.
The collision just happens at the surface level, so the material underneath doesn't see any effect.
I don't know why we didn't start using cold spray years and years ago. We're an aviation company, and we've evolved from brokering of parts into maintenance of parts. We used to use welding, and we had a lot of distortion, so we started looking at other options. And our engineering department came up, well, what about cold spray? The number of repairs we could do would be huge.
If I make a machining mistake on a detail, drill a hole in the wrong spot, machine too much material off, in the old days I may scrap it. Today I can spray SST technology and basically I have a reusable detail.
In certain situations, cold spray is your only option. Cold spray is saving a part that the OEM might charge you $30,000 for, but we can repair it for $7,000.
The tool and mold industry, for example, have to make adjustments to very expensive molds that can be in the hundreds of thousands or even millions of dollars. Because the SST technology highly complements aluminum, which a lot of molds are made from, we're able to go in and help them mitigate some of those issues.
I think it's very cost effective. I mean, based on the cost of these parts from the OEM, and especially the parts that we do, the OEM doesn't produce these on a mass scale anymore. It looks better than new. I've heard that said several times when we give them back. This looks better than the new product we get from the OEM.
To give you an example, we had a large OEM that made a pretty critical error on a high-value component. They had 10,000 of these, and they found out about our solution, and because it's a portable solution with our SST P-Series, we were able to go in and save the component, saving them millions and millions of dollars.
More than 30, 40 different repair parts has been approved by FAA.
We deal with the FAA, we deal with the European aviations. You put out a quality product and people trust what you're doing.
We supply everything from the applications to the base materials to the equipment that actually does the spraying. So we're really full service in that regard.
When we have issues with the cold spray, with the equipment and everything else, we call them up and ask for their advice.
There's always a pretty fluid exchange of ideas with our clientele and academia to help find its place in the market.
There's an evolution, every time you're working to get it better and better and better. We want to solve problems. And that's basically what Centerline is all about.
I'm very happy with Centerline.
If you look at the number of applications that have been approved for cold spray in the last 3 to 5 years, the curve is starting to get logarithmic.
Okay, so our next speaker is Dr. Rhys Jones. He's from Monash University, and he's a fellow that I've worked with for a number of years, and he's very instrumental as we venture into structural repair and additive manufacturing of 3D printed parts. And the reason being is because we're going that next level of scrutiny, of ensuring integrity, of more in-depth analysis of properties such as fatigue and fracture. And his work speaks towards that. His work involves determining crack growth rates, fatigue and fracture. And as we venture into load-bearing applications, fatigue applications, this is the type of data, we talked about data extensively, this is the type of data that's required to qualify such applications. So obviously Monash University is Australia, with travel restrictions, his presentation is pre-recorded. I don't know if he'll be available afterwards. Do we know that for? He usually is, because I've worked with him for years. The guy, I don't even know if he sleeps. So I guess we'll cross that bridge at the end of his presentation.
What I hope to do in this talk is to illustrate how to perform a durability economic life assessment of cold spray repairs. Our previous work has illustrated the durability and damage tolerance of cold spray doublers. We validated this via tests on a full-scale F-18 center barrel subjected to representative operational flight loads. In this test, the doublers lasted 3 lifetimes, whilst the aeroplane fell about around it. Even after 3 lifetimes, there was no cracking in any of the doublers or any delamination whatsoever. In the case of skin corrosion on compressive surfaces, where there's up to 50% loss of material, we've shown that cold spray repairs can restore the load-bearing capacity of the wing. We have also shown that cold spray repairs to stress corrosion, cracking, and risers on compression surfaces can restore the load-bearing capacity of the wing. This talk builds on those developments, and we illustrate how to perform the durability economic life assessment that is mandated in the United States Joint Services Structural Guidelines, JSSG 2006, Mill Standard 1530D, and USAF Structures Bulletin EZ 1901. Before we can discuss how to perform the durability economic life analysis, it's important to note that the requirements for the airworthiness certification of military aircraft are delineated in Joint Services Structural Guidelines, JSSG 2006, Mill Standard 1530D, and for cold spray repairs in United States Structures Bulletin EZ 1901. The 2009 report on the annual cost of corrosion estimated that corrosion costs between $10 to $20 billion in the US DoD. In the case of USAF, these costs were roughly 30% of the total maintenance cost. A similar study has been done in Australia. One of the problems we have, whether you're talking about Navy, Army, or USAF airplanes, is that parts can take a long time to reach you, typically between 9 to 12 months. Can't have your airplane unavailable or your weapon system unavailable for that amount of time. Consequently, cold spray offers a marvelous way of achieving increased availability. The situation with respect to cold spray repairs changed dramatically in 2019 when the Undersecretary Acquisition and Sustainment stated that AM parts or AM repair processes, such as cold spray, can be used in both critical and non-critical applications. He also stated that for all applications, the appropriate level of qualification, certification must be as per the engineering support activity. In other words, the airworthiness or the application of cold spray to load-bearing structures requires a durability analysis. Before proceeding, it's necessary to introduce the definition of durability. The definition is given in JSSG 2006 and also in Mill Standard 1530D, and it's on this particular slide. In this context, USAF Structures Bulletin EZ 1901 stated that the most difficult challenge facing the implementation of AM and cold spray repairs is to establish an accurate prediction of the structure performance specific to durability and damage tolerance. Okay, so let's get down to the nitty-gritty. I'm now going to explain how to actually do a durability analysis of a cold spray repair, in this case to corrosion damage in 7075 T7351. Geometry and the extent of the corrosion is shown in the slide. I'm going to discuss test results obtained for 2 specimens. The labeling of these 2 specimens is also shown on the slide. Specimen was subjected to marker block loading. The reason for that is we want to be able to do fractography on the test specimen. It's important to recall that cold spray coatings are inherently damage tolerant. That is, if the application process is done properly. In this example, which is taken from the reference at the bottom, you see 7075 powder coating on a 7075 T7351 aluminium alloy substrate. The notch is cut into the cold spray coating. What you see is that not only does the notch not result in cracking at the stress concentrator in the notch, but that cracking in this instance and in many others occurs well away from the notch. Furthermore, the initiation of the cracks is in the 7075 T7351 substrate. Crack initiation, fatigue crack growth, nothing to do with initiation in the cold spray coating. Furthermore, you don't see cracking or delamination in the coating until late in the test. The next slide has more examples that show the sensitivity of the substrate is greater than the fatigue sensitivity of the cold spray. The 2 examples on this slide show what I discussed above in spades. In other words, you can see where the cracks initiated. Not in the cold spray, but in the substrate at the interface between the cold spray and the 7075 T7351. In the 2 examples I'm showing in this slide, you can see that there are a number of cracks. One case 4, the other case 2. By using fractography, we could measure the crack growth histories in both cases. So, how are we going to do the durability analysis? Well, it's now known that the growth of long cracks and small naturally occurring cracks can often be expressed as per the Hartman-Shivey variant of the NASCAR crack growth equation. Equation 1. The term delta kappa, the characterizing force, is the Schwalbe crack tip similitude parameter given by equation 2. There are 2 constants here, threshold and A, the cyclic toughness. There's a slight difference between the threshold term and the ASTM term. And the difference is given in the next equation. More details on this particular crack growth equation are given in the references. The crack growth equation for small naturally occurring cracks in 7075 T7351 can be expressed as per equations 1 and 2 on this slide. And for this problem set, the value of the apparent fracture toughness is 111 MPa root meter. Joint Services Structural Guidelines suggest using an A-basis property. The A-basis property for durability analysis lies in the range 0.1 to 0.3. The references for this are given in the slide. This is all taken from previous work, and hence we're going to use this to perform the building block approach required in the durability analysis. The bottom line is when you proceed in this fashion, that you accurately compute the crack growth histories for each of the 7 cracks in these various specimens. What this means is that you've performed an accurate durability analysis. Okay, so let's try and draw things together. The excellent durability and damage tolerance of cold spray doublers has previously been validated via full-scale fatigue testing on an F-18 center barrel under operational flight loads. We've also shown previously how cold spray repairs to skin corrosion on compression surfaces can restore the load-bearing capacity of a wing. Similarly, we've shown how cold spray repairs to stress corrosion cracking in risers on the compressive surface of wings similarly restores the load-bearing capacity of the wing. This talk has taken the science one step further because we've shown how for cold spray repairs on tension-dominated surfaces to perform the durability economic life assessment that is mandated in the U.S. Joint Service Structural Guidelines, JSSG 2006, Mill Standard 1530D, and United States Air Force Structures Bulletin EZ 1901. So, are there any questions?
Thank you, Reese. I got your message. You don't sleep. I was right. So do we have any questions for Dr. Jones? I like saying Dr. Jones, like Raiders of the Lost Ark. Yes, sir. Okay, so the question, Reese, is how do you take into consideration crack initiation for the DADN?
Can you hear me? Hello, can you hear me?
Yes, so let me ask it again. How do you take into consideration crack initiation for your crack growth studies?
I'm speaking. Can you hear me? Hello?
We can hear you.
Good. Okay. If you read the certification standards that specifically talk about the USAF EZ Structures Bulletin EZ 1901, you are required to assume an equivalent initial defect size or an EADS. The sizes mandated come directly out of the Joint Services Structural Guidelines, JSSG 2006. So the question of initiation ceases to exist. Now, having said that, the analysis automatically takes care of initiation. And you can include the initiations. The analysis you've just seen on the screen includes computing all the initiation times. So the analysis does the initiation from the measured material discontinuities. However, the certification standards don't allow you to take into consideration the time from initiation to the time for EADS. Now, that may be different in the Civil Aviation Authority, and I'm not quite sure whether the U.S. Army follows the Joint Services Structural Guidelines documentation or not. Victims probably would be more up to date with that.
Okay, good. Very good. Thank you. That answers it. I got the thumbs up, Reese. Any other questions internally? External, Aaron? External? Okay. I'll ask a question, Reese, in the meantime. So besides the 7000 series, have you looked at like the 6000 and the 5000 series?
We've looked at 2000 series and 2000 and 7000 series, but not 6000 and 5000 series.
We have one more.
Do you have any idea why the substrate should be more susceptible to fatigue initiation, even though it's the same alloy?
Yeah, that's a good question. So, do you have any idea why the substrate would be more susceptible to crack initiation as opposed to the cold spray deposit, since they're both the same material?
Absolutely. The residual stress is imparted in the substrate. Basically, I'm going to be very rude and very crude. Basically, they fuck up any crack growth in the substrate in the cold spray. If you do it properly, and that's the whole thing. If you do it properly, the only thing that cracks is the substrate, and it doesn't delaminate. And this is not just this is dot one. We would have done close to 100 tests. It doesn't crack. It doesn't delaminate.
I think he's pretty sure of himself. No, I'm just kidding, Reese. No, I think I heard some Australians swearing. No, I'm just kidding. He's laughing. He's laughing. So, no, and you know what else, too, I'll add to that, Reese, is grain refinement, right? You take a look at the grains of aluminum, right? They're huge. And what do we know about, fatigue, fracture, fine grain refinement? Yeah. All right. Well, I'm going to bid you, 14 hours, right? So, good night.
It's 3 in the morning.
Thank you, Reese. Talk to you soon.
Bye-bye.
All right. So our next speaker is from Germany, and his recording his presentation rather is pre-recorded, and unfortunately he won't be available. He's not a night owl like Reese is. It's tough making these agendas and taking into account all of the, because I have, Australian folks and people from Germany. I don't know if we have the UK this year, but yeah, we do. So, but this is a presentation that I've been waiting for, and I bet you a lot of folks here have been as well. Oliver works at Siemens, and he's going to talk about software development specific to 3D printing.
The great progress of cold spray equipment and process development during the past 2 decades has been accompanied by impressive improvements on the ancillary side, namely robotic automation. Automation is key for extended industrial deployment of cold spray also outside the well-established sectors of military and aerospace applications. Automation is not only required for serial production. It is also necessary for achieving accuracy and reliable quality in customized manufacturing or repair. The hassle, as SP3D put it, with automated cold spray production is mainly the robotic programming. In fact, the leap from producing test sample geometries towards programming cold spray runs for industrial coating, 3D printing or joining applications may be huge. In the laboratory, it is often sufficient to produce a chunk of good material and shape it by subtractive machining. The accuracy demands to robotic calibration are moderate in this case, and the kinematic programs are, more or less, easily written at the shop floor. Once a cold spray procedure has been developed to the point where material quality meets specification, the transfer from test coupons to a potentially complex workpiece shape may emerge as a bottleneck. We have encountered cases where the demand for cost-prohibitive programming eventually hindered the process from arriving at the shop floor. Cold spray requires to coat areas line-wise, while keeping standoff distance, lead and tilt angles within a narrow process window. This property imposes constraints on the feasible tool path and may result in complicated robotic moves. NX can automatically generate the toolpath from a CAD model. Let us look over Aline's shoulder for 5 minutes to see how easily this is accomplished. She begins with setting up the cam session.
The latter comprises a digital model of the machine, including its kinematics and the post-processing. In our case, we use a KUKA KR60 6-axis industry robot combined with an external axis, a positioner with a rotary plate. After the CAD model of a workpiece has been added to the cam session, it is placed in the preferred position by applying suitable constraints. Thus, turbine plate and its support are stacked in the center of the positioner table. In order to calculate paths along which the tool is to be moved, affected surfaces and guide curves need to be defined. The selection of surfaces is possible by different methods, such as specifying single surfaces or tangential surfaces. To allow for correct tool movement, ensure positive orientation of all contiguous surfaces by picking the correct orientation of their normal vectors outward. As for surface selection, there are various possibilities to select the guide curves. Moreover, curve manifolds can be defined. Again, attention needs to be paid to select the appropriate curve orientation. Beyond the tangential traversing speed, the cold spray process typically requires full control of the accompanying tripod along the entire tool path. NXCam allows for separate specification of local lead and tilt angles with respect to the local surface normal. These angles can be set in the multi-axis deposition module and the freeform additive coating section. Once the surfaces, guide curves and tools have been selected, the path properties can be determined. The triering strategy needs to be defined in accordance with the given component shape and the surface topology. In our example, the surface region to be coated is homeomorphic to a cylinder surface. The spray tool is to be moved primarily in the circumferential direction around the airfoil. Secondarily, it is to move in vertical direction following either a helical line or a vertical stack of tracks, each alternating in direction. Further parameters having to be set comprise basic coating properties such as the single path thickness and total layer thickness, the path start and end points, path overhangs, and geodesic path separation distances. Finally, specify the order in which the paths are to be generated. The ordering scheme can vary between surface regions. Once all settings have been made, the path is calculated and visualized in almost no time, allowing the user to verify the result. Arrival and departure paths, as well as transfer moves between separate path segments or surface regions, are determined by means of non-cutting moves. Complex surface shapes sometimes require combinations of several tool pathways. NXCAM allows for generation of separate paths, for example, one along the blade airfoil and another on the adjacent platform surface, which subsequently can be linked by appropriate transfer pathways. After the toolpath programming has been completed, it needs to be specified how the robot should drive the tool along the path. In NXCAM, this can be done using the robotic rules. The robot needs to know how to orient the tool during the coding process and which axis configuration to use for positioning the tool. Also, the approach and departure positions, the orientation of the external axis, as well as motion speeds and motion types need to be set. Movement instructions to choose from comprise point-to-point movements and linear path movements. Point-to-point commands generate black box direct movements toward the goal position, with the robot choosing the fastest possible way. On the contrary, linear path movements ensure that the tooltip moves along a straight line, with position deviations within a defined tolerance range anywhere. The approach and departure positions at the beginning and end of the coding process respectively are reached by point-to-point movements, whereas the tool path across the coding region and the transfer paths are traversed at varying locally defined speeds with narrow position tolerance as defined by linear path movements. All settings can be visualized, checked and edited in the robot control interface. The tooltip trajectory thus is a polygon approximation of smooth coding paths embedded to the component surface. The integrated simulation module supports final assessment of the programming result. When the simulated tool motion looks right, the post-process can be started. Eventually, the NX post-output file can be uploaded to the controller of the real machine tool. Then, the manufacturing process is ready to run on real. The NX library provides a set of different post-processors. Using the post configurator, existing post-processors can be edited or new post-processors can be created and implemented in NXCAM.
The generic NX animation is a pure kinematic visualization of the toolpath geometry, which does not capture the motion speed. Several machine parameters defining the kinetic capability of the KUKA robot are not included in this simulation. Therefore, the timing of certain moves is unrealistic. The true robot motion results from combination of the true machine parameters with the output of the NX post-processor for the KUKA robot language KRL. Details of approximate positioning or flyby motions, for instance, cannot be predicted at this level by NX. To obtain a realistic machine simulation, the KRL code produced by NX could be executed virtually in the vendor software KUKA Sim Pro. An alternative workflow is possible when Xenumeric with the extension RunMyRobot is used as motion controller. The package offers the advantage that an NX program for a spray process can still run on the robot after recalibration or minor tool changes. Xenumeric takes standard NC commands as input, which are obtained as output from the NX post-processor. A realistic machine simulation is provided by the virtual Xenumeric machine VNCK. It is integrated in NX and enables a seamless workflow from toolpath generation to process run simulation. We show a little example in the following.
In this use case, a repair task is to be accomplished using cold spray. There is a groove located on the cylinder surface. The side walls of the groove are inclined at a 70-degree angle relative to the surface normal of the cylinder. This V-groove shape requires a certain toolpath strategy, considering the local surface inclination to evenly fill the groove with repair material. A spiral movement of the cold spray nozzle around the cylindric component presents a suitable driving strategy. The starting point for the repair process is placed in the center of the groove because they are the steepest and requires the most material, that is, the most repetitions of the deposition path. Starting from this point, the tool is moved on a helix-shaped path. The first winding is in upward direction. 2 windings in downward direction follow, then 3 windings in upward direction, and so on. Following this pattern, additional windings are iteratively programmed until the tool traverses the groove completely from the top to the bottom. The relevant workpiece surfaces need to be assigned to each winding according to their position. Then, all windings need to be linked with one another so that a connected tool guide regarding the groove is generated. A spiral path that repeatedly crosses the center of the groove and is extended outwards by 1 winding distance before each turning point. Since all tool speeds and orientations with respect to the workpiece surface and all applicable robot rules are already set, the simulation can be started now. At first, we run the NX toolpath simulation, which is helpful to visualize the deposition of sprayed material in the V-groove. The motion timing of this animation is not necessarily realistic, but the sprayed track is. At this point, we stop the toolpath simulation and switch to the machine code-based simulation by the VNCK virtual machine. VNCK opens a virtual user interface of the Xenomeric. Xenomeric manages all available tools such as different cold spray nozzles, powder injectors, and stagnation chamber extensions. The tool selection has been made in the early stage of toolpath programming. It is only reviewed here but not altered. Now we can start a realistic process simulation including all auxiliary moves. Bottom left we see the machine code line currently executed. Next to it we see the axis position and velocities. On the right hand side the tooltip motion speed is continuously displayed.
In our laboratory in Berlin, we run the 13-axis system shown on the right-hand side. On the photograph, 2 cold spray torches were mounted on the 2 6-axis Komao robots, and a workpiece is mounted on the 13th axis. The installation shown here serves for development of multi-axis operated additive manufacturing or local repair processes. To control the robotic motion, we use NX-Cam. It calculates the tool path from the CAD model and passes the motion commands directly to the xenomeric controller of the Comau robots. This connection allows for offline programming of the kinematics and circumvents potential difficulties arising at the interface between a robot's command language and the output of a CAM system. The Siemens software yields a complete toolchain. As an example of net-shape additive manufacturing, we show an existing 3D printing process for copper in the mirror of NX-Cam simulation. Along the spray path, the nozzle maintains constant standoff distance, constant tangential speed, and piecewise constant lateral tilt angles. The productive spray path remains of pairs of rails. Frequent repetition of the shown motion pattern makes the rails grow in height. Hereby, they form vertical walls with a flat top. The resulting cross-section shape is rectangular, with slightly rounded corners and an aspect ratio greater than unity. The tilt angle specification, in connection with uniform rail separation, is crucial for the net shape obtained. On the cold spray process control side, Siemens Technology has developed a gas flow monitoring system allowing real-time detection of nozzle clogging. This system allows observation of flow corruption in an early stage, before it manifests by receding particle velocities compromising the quality of the workpiece. Nozzle clogging occurs when spraying certain metal powder materials at elevated gas temperatures. The phenomenon is the catastrophic end of a long-lasting process which commences imperceptibly. Powder particles randomly striking the nozzle wall in the divergent section little by little form an internal coating, gradually increasing the wall roughness. The roughness continues to grow in a stochastic manner until few nucleation sites form which efficiently capture impinging particles at increasing rates. Some of those material pile-ups may erode subsequently, but eventually one of them will block a significant portion of the cross-section area. None of the proceedings can be sensed by the cold spray system control until the choking cross-section diminishes due to massive blocking. The changes take place in the supersonic section of the flow, from where no information can propagate backwards to the stagnation chamber where the temperature and pressure sensors are located. Nevertheless, the particle velocity at the nozzle exit starts to decrease well before the final clogging. When the nozzle wall ceases from being hydraulic smooth, the internal boundary layer grows, dissipation increases, and the effective expansion ratio drops. Transient changes of the flow direction may occur. Continuous observation of the after-nozzle flow by the Siemens monitoring system reveals such erratic flow periods, signalizing imminent clogging well before particle velocity drop becomes critical to part quality. The system recommends when to shut down the cold spray system for nozzle change. It helps to exhaust the operation span of the nozzle by indicating the right moment to stop spraying. In addition to this flow monitoring system, Siemens Technology has developed inexpensive refurbishment procedures for clogged nozzles. The careful removal of debris makes it possible to reuse the nozzle. In combination, the two technologies render cold spray productive, reliable, and affordable, even when using feedstock with pronounced clogging tendency. Although today's presentation puts some emphasis on kinematic programming, the recipe for success in industrial cold spray application lists a few more ingredients. Our experience with cold spray helps to create a cost-efficient workflow at the shop floor and to assure permanent quality of both the process and the product. Siemens Technology is active in R&D of cold spray since 2005. Potential applications of cold spray have been evaluated technically and assessed cost-wise. Owing to the unusual diversity of Siemens' product portfolio during the past 15 years, we ran projects related to power generation, transmission and switching, electrical machines, oil and gas, or steel making. After having conducted 80 cold spray projects at Siemens, it is common to us to learn our customers' language and thinking. In most cases, cold spray competes with qualified procedures. Any expected advantage needs to be balanced out with the risk of introducing a new technology and supply chain. In response to this challenge, we pursue agile collaboration with our customers, joining forces of the domain specialists and the cold spray experts. We thank for your kind attention and look forward to getting to know your thoughts.
So we've got a special case here. So Oliver is with us live, but he's only taking questions via email, so not live. So he's up listening to us, but there's a link, and don't be listening intently to me unless you're on your computer, because that's the only way you're going to be able to ask him questions. We can't hear in our internal meeting unless you're on your computer. So it's all those hundreds of folks that are virtual that are listening to me. They can feel free to email Oliver any question under the sun, and he'll get back to them. He's probably going to wish he didn't say that, but that's how he chooses. So anyway, we thank him. I really wish you were here. He's spoken in the past. He's a very good He's a very good speaker, and he's very technically astute, extremely so. And I admire his work, and we look forward to maybe getting back to normal next year. So I want to keep us on track, keep us going. I hope Ozan's here. Yep, I see Ozan. Dr. Ozan Ozdemir from Northeastern University is going to be talking about advancements in machine learning, automation, and I'm going to let you take it away.
Hello, everyone. Good day to everyone from all over the world. My name is Ozan Ozdemir. I'm a research assistant professor at Northeastern University in the Department of Mechanical and Industrial Engineering. My talk today is titled Intelligent Manufacturing Cells for Modern Cold Spray. And I'll be presenting the work of myself and my colleagues who are listed on the slide here. Just a quick intro to what we do at Northeastern University in regards to cold spray research. We have a very wide spectrum of expertise in solid mechanics, fluid mechanics, material science, robotics, and machine learning. And we've been applying our expertise to all aspects of the cold spray research. And we do this to advance the technology so that it can become more reliable, more repeatable, and we can extend the reach of cold spray to a lot of different applications. And that includes additive manufacturing and 3D metal printing. There's a little bit of delay, I think. Let's see. Yeah. Oh, yeah. Cold spray has about 2 dozen parameters that you need to adjust so that you can get a product with the properties that you desire, and to be able to intelligently make decisions so that we can get a product that's high quality and we can use in any application that you want. you really need to integrate some intelligent decision-making tools that you can use across the cold spray field from powder to part. And I'll show you some of the work that we've been doing as far in regards to these tools in powder feedstock, the cold spray process control, and manipulation of the material buildup for additive manufacturing and repair. All right, feedstock control. As Vic mentioned yesterday, powder feedstock parameters are probably one of the most important parameters in the cold spray quality control in general. And powder feedstock affects your fluid dynamics, and it affects the solid mechanics, the deformation of the particles, and it also affects the final microstructural properties and mechanical properties of your cold spray products. These powders come in all sizes and shapes, and there are several different additive manufacturing processes for manufacturing these powders. And most of these we use in cold spray are gas atomized. In a lot of cases, they're assumed spherical for modeling purposes, for process optimization and such. And current standards call for several parameters, specify several parameters so that you can qualify it for your process, including heat treatment, size distribution, flowability, and some other mechanical and metallurgical properties. However, particle shape specification from a quantitative standpoint is not really one of them. And in recent studies that we've conducted, this appears to have implications on impact velocity and temperature. All right. When we look at some of the common powders that we use, even what we see is that even the gas atomized particles have some volume of particles that are not perfectly spherical. Even the particles that we assume to be spherical, for gas dynamics purposes, we specify the sphericity of particles. This is a parameter that we use to compute the momentum of particles in the fluid dynamics stream. The sphericity parameter is denoted with psi. This is a fairly complicated parameter to measure using your standard methods. And a lot of times, this parameter is simplified. And for a first level analysis, we've been using the ratio of the nominal diameter of particles to the major axis length of the particles. And the psi parameter, if it equals 1, it's a perfect sphere. If psi is less than 1, it's more and more off spherical. And looking at the powder batches that we commonly deal with, what we see is that there's a large volume of particles that are non-spherical, and this particle sphericity goes all the way down to 0.5 and so. And in the fluid dynamics regimes that we deal with in cold spray, this type of particle sphericity actually makes a huge difference in particle impact velocity and a little bit of difference in particle temperature. And I'll show you how much difference this makes. And also, I just want to mention, there's a size dependence of particle sphericity as a nature of these manufacturing processes. All right, I see that you guys uploaded my old slides, but just to show you the implications of particle sphericity, we looked at a couple of different scenarios of spraying aluminum in the VRC system with nitrogen, and also spraying copper powder, Praxair gas atomized copper powder in the SPEED3D system, and looked at perfectly spherical, and put the measurements, hundreds of different measurements of aluminum and copper particles, their size and sphericity into high fidelity computational models. And first we assumed perfectly spherical particles, and then we put in the measured particle sphericity into the models to observe the effects of particle sphericity in the velocity of particles at the exit of the nozzle. And we compared the model outputs for perfectly spherical and non-spherical particles with the measurements of particle velocity using an OSAIR high-watch HR1 system. And I'll show you the results here. The first results from the VRC aluminum spray measurement is you can see right here. What you see here is the blue dots are the measurement results, and the yellow is the estimation of the 3D CFD simulation. What you see is that the simulation underestimates particle velocity significantly, and the variation of particle velocity is not captured. But when we put particle sphericity into our calculations, what we see is that we're capturing both particle velocity accurately along with the variation of particle velocity all across the particle size spectrum. And we observe the same thing when we repeat it for a completely different process and completely different machine. We see that from underestimating particle velocity, we go to very accurately estimating velocity and the distribution of velocity as well. And so this means that we really need to take into account particle sphericity when we do quality control in our laboratories, in our field facilities and such. And if you want to double check, if something's not going right with the powders that you're receiving, this might be one of the parameters that you might want to check, because it has really strong implications on the final particle velocity and the final process in general. All right, I'm going to go into the work we're doing in regards to the cold spray process control. So when it comes to the cold spray process control, aka the gas dynamic control, and trying to make sure that your process is as good as you think it's going to be, one of the most powerful tools we have in our belt is particle velocimetry. However, and especially the particle velocimeters that can measure size along with particle velocity, okay? And we really need to make sure we're analyzing the data from these velocimeters accurately. Although these systems generally are very accurate in measuring size and velocity, they may not be capturing the entire size distribution of your powder batch. And so you need to really be careful as to analyzing size and velocity concurrently so that you're making sure you're comparing apples to apples when you look at the velocity data. To demonstrate this, we performed a quick study. We sprayed copper powder using the VRC Gen 3 system at identical conditions 6 separate times and 6 different days. And what we saw was that for 4 of these cases, the average particle size along with average particle velocity was coming out to be about the same. But for 2 cases, the particle velocity was different, but also looking at the particle size was also different. So this means that we can't really make an apples-to-apples comparison just by looking at the velocity, as the size distribution we're measuring in these 2 cases are probably different. And we also see that in the top right plot. So what we need to do is plot the curve of particle size versus particle velocity, and you can make a more direct comparison using a plot such as this. In the bottom right plot, what you see is a moving average of velocity with respect to particle size averaged at 5 micron intervals. And what you see here is that the 2 cases, in fact, are giving us lower velocities across the particle size spectrum. Particle velocimeters are also, these in situ particle velocity measurements are also very good for running parameter sweeps, whether you're trying to make sure that your system is working properly, or whether you're trying to develop a new process and you want to dial in your particle velocities. you need to still be able to measure mean particle size along with mean particle velocity. And you want to make sure that your particle size for the same batch of powder is the same for the different cases you're running. And in these 4 different cases, what we're looking at is we're increasing gas pressure and temperature. We would expect particle velocity to increase, but since we're using the same powder batch, we would like the particle average size to come out to be the same. And so in this particular case, we're seeing exactly that. Particle size is staying about the same, but particle velocity is different. So we can, in this particular case, make an apples-to-apples comparison. But still, particle size distribution that is measured in these particular cases may not be an exact comparison to the size distribution that you have in your powder batch. So it's always good to take a look at your size versus velocity curves and see how the velocity is increasing across different particle sizes. So again, just to conclude this particular study, velocity is dependent on particle size. We need to couple particle size measurements along with particle velocity measurements to become more confident in our analyses. And size distributions from velocimeters may not be representative of the actual particle size distribution, so systems capable of accurately measuring size is valuable for measurement confidence. We're also using multi-scale advanced models to help guide us with equipment and process design. Particle velocimeters are great tools, but they do not give us what really particles are going through upstream of the nozzle exit. And we do not use these particle velocimeters with a substrate in presence, so they don't really tell us exactly what's going on at impact. So we implement these multi-scale models so that we can understand what's going on when the particles are injected, how they're flowing through our nozzle, and what the particle impact conditions are. And these are great tools for both equipment design and understanding complex fluid behavior, so it can help us guide our process. These models are also helping us control the deposition shape for additive manufacturing. I'm going to go right into what we're doing to control material buildup. So in order to control additive manufacturing process and material buildup, we have been working heavily on this particular topic over the past several years. And I'm just going to give a few examples of what we've been doing in deposition process control. And these topics will be related to the nature of material buildup and manipulation, understanding the deposition of materials onto different types of features, and understanding thermal history of a cold spray product so that we can make informed decisions about how we build materials, and implementing in situ measurements into our cold spray process for superior process control and cold spray and producing superior cold spray products. All right. As a result of any given cold spray process, we get a deposition footprint, and this footprint is generally in the shape of a bell curve or a conical shape from an axis symmetric nozzle. And when we traverse the nozzle, we get this line deposit, and then you manipulate the source, the footprint source, and you end up getting a deposit that you can control, and we can build complex and simple geometries. However, we really want to be able to understand the nature of a deposition process by integrating sensory systems into this, so that we can have a more informed understanding of the material deposition process, so that we can have better printing control. To this end, we've built an in-situ deposition measurement system. This is an optical system that we integrated with our 6-axis robot in our cold spray laboratory, and you're seeing a demo of the sensory system scanning a part that is on our turntable, and you can see the scan happening in virtual space as well as in real time. We're using these deposition models to build predictive deposition models that are very accurate, and you can see an example of one of these models in the top right, and you can see the comparison of measurement versus model prediction in the bottom for a different case. Again, we'll be using this type of an integrated in-situ measurement system for building reliable material deposition models. We've already started integrating these models for building predictable shapes. And these types of models will help us build toolpath plans so that we can build more complicated 3D printed geometries. We're also coupling this work with some modeling efforts, and this is an effort with the Army Research Laboratory. What we're trying to do is understand how materials build in features and how the gas dynamics are affected when you have different types of geometries, and this is going to become really, really important for 3D printed parts because you're continuously changing the surface geometry. In this particular example, we're showing the deposition of particles into a trench and also into a wedge. And these represent 90-degree corners that we see regularly. We are integrating, we've built an optical system in our laboratory to be able to visualize the gas impingement on a substrate, and so that we can also see how the gas dynamics are behaving on different types of surface geometries. And this is going to really be helpful in dialing in what kind of tool paths we need to follow to fill in corners and how to better build materials into different geometries. In another complementary work, we've integrated in-situ measurements of infrared thermal imaging systems, and we're using these system to understand the thermal history so that we can build process and property relationship. And we're coupling this effort with finite element methods models so that we can understand what's going on during the deposition, so then we can understand what we're ending up with at the end. And this is particularly important for residual stress buildup. So we built several different types of in-situ measurement systems. We're also incorporating deep learning methods, machine learning methods, so that we can use these types of systems dynamically during a cold spray process, so that we can monitor our process and also detect if there's any anomalies. And we've had quite a bit of success doing this, and we'll continue to be working on this. All right. Going forward, we're going to continue to integrate measurement capabilities throughout the process. We'll be coupling these measurement capabilities with advanced models, and we'll be developing informed 3D printing and repair procedures for cold spray. And this is going to really help us bring automation, repeatability, and reliability to modern cold spray manufacturing cells. And with that, thank you for your attention, and I'd like to thank all of my co-authors and our sponsors and partners. And I'll take any questions. Yes.
With the deep learning techniques you guys are using,
Yeah, so with the machine learning models, what are some of the features we're putting into the models and what we're trying to get out of it? Is that right, Aaron? We're using, again, we're using this information several different ways, and it's deep learning, so we're actually trying to put in comprehensive information. We're trying to put in, it's a thermal image, we're putting in the entire thermal image, and we're trying to get out of it whatever, we're first teaching the algorithm what the normal process should look like, and then we're trying to learn from, we're controlling the process to understand. We're running controlled experiments so that we can learn how that image changes in different scenarios, so that we can understand if anything is different, and if anything is different, what is different. Yep. Yes.
What does your presentation today represent in terms of time and your staffing and complementing with your professional staff and then the student involvement at your university? Is this a one-year project, or if I came here before COVID, you wouldn't? I know that's not. But just to be realistic,
What type of time it's going to take, or how long we have been spending?
What do you represent today?
Oh, this is years in the making. I guess we built our lab, 5 years ago? But I've been working, we've been working
together, yes.
for nearly a decade.
Ozan was a student that I mentored at South Dakota as undergrad, and then grad, and then he's postdoc, then he's associate professor. So this is a culmination of all those years.
Yeah.
Tom.
Yeah. Any other questions?
Tom.
Hey, go ahead, Tom.
Quick question on the visualization of the cold spray buildup. Does it account for stuff like shadowing or overspray at bad angles? I asked because when we're doing complex geometries, the two things we run into a lot are the cold spray self-shadowing during buildup, so you end up with hollows, or coming out of the overspray and ending up causing the delamination layer when we try to build up over it.
So the question was whether the deposition buildup measurement system is accounting for shadows and shadowing and things such as this. So we're actually using this process to learn the deposition shape buildup, and so because in a situation where you would have shadowing and things like that, the measurement system becomes a little too bulky. So we would take that out in circumstances such as that. But if you have a process where you can manage the motions of the sensor with the robot, then you can leave it in. But in those cases, I think we can scan almost everything into the virtual space. Yep. Any other questions?
Anything? Okay, good.
All right.
Excellent. Thank you. Excellent. So